Okay, I'm going to do problem number 1. So it's incomplete. The way it's stated is incomplete. The way that it is stated is incomplete. So this should say the hemisphere y is greater than or equal to 0. So if you didn't do that, if you didn't understand what I meant by this, which there's no reason you should probably pause and try to do this problem before going on. Okay, so this is the problem I'm going to do. Number 1. Okay, and this is a Stokes theorem question. Okay, so what's the idea here? So the hemisphere, we have the circle x squared plus y squared plus z squared is equal to 16. This is a sphere of radius 4 centered at the origin, and we just want the part y is greater than or equal to 0. So the boundary, so what does Stokes' theorem say? It says that this integral is equal to the integral over the boundary curve of f, the line integral over the boundary curve of the vector field. Okay, so we're going to do this problem in 2 steps. So first we're going to do this step, and we're actually going to convert this back to a surface integral, but over an easier surface. And so once you kind of get the idea of what's going on here, you can skip this intermediate step. So what is the boundary curve of this surface? Well, if we look in the x plane, the xy plane, this is x, this is y. Okay, so the projection of this shape onto the xy plane is a circle of radius 4, or that's a disk of radius 4. And so this is the boundary curve. Since we want outward orientation, it means we want to have a counterclockwise orientation on this circle. Okay, and so what this says then is that the surface integral of the curl field that we want to compute is equal to the line integral of the function of the vector field f dotted with dr over this circle of radius 4 in the xy. Sorry, this is the z plane, in the xz plane. Okay, so now we completely forget about doing the surface integral of the curl field over this hemisphere. We don't think about that anymore. Now the problem that we're working on is doing the line integral of the vector field around this circle here. Okay, but now we can use Stokes' theorem, because what is a surface? What is the most obvious surface whose boundary is equal to this circle? Well, it's just going to be the disk of radius 4 that it encloses, this disk right here. Okay, so what do we know then? The line integral of this vector field around this curve is going to be the surface integral over this surface. I'll call it S1 since we're calling the other surface S, of the curl of F. Okay, so now what we want to do is compute the surface integral of the curl of F over this surface. Okay, well, what is this? Well, I will leave this to you to determine the curl of F, or at least verify that what I'm saying is correct. The curl of F is equal to zx cosine y e to the y minus z sine z, and then, whoops, I'll just write the third component below. The third component is cosine y minus z e to the y. Okay, that's the curl of f. Okay, so how do we define this? This is equal to the integral, the surface integral of the scalar field curl of f dotted with the outward pointing normal vector ds. Okay, this is just how we define the surface integral of a vector field. We define it in terms of the surface integral of a certain scalar field. Here, n is the outward pointing normal vector. Okay, or n is the normal vector that is consistent with the orientation on this surface, or on this circle. So what is that going to be? Well, it's going to be the normal vector that points away from this surface that's perpendicular to the zx plane. So that's just going to be the vector 0, 1, 0. And if you don't understand why, just take a moment to think about it. So n is the normal vector 0, 1, 0. So what is the surface? The surface is this green disk here. This is in the xz plane. So the normal vector is either going to be 0, 1, 0 or 0, minus 1, 0. Since we want the outward pointing orientation, it's going to be 0, 1, 0. Okay, so this quantity right here, the curl of f dotted within, the curl of f dotted within, well, notice that all that's going to be is just the second component of the curl of n, because when you do the dot product with 0, 1, 0, the only term that survives is this e to the y, this is e to the y z sine y. So this is e to the y minus z sine y. Okay, so then we want this surface integral. So then this right here is equal to the surface integral of e to the y minus z sine y. Okay, but notice on this disk, y is equal to 0 because this is in the xz plane. So the disk on this disk, y is equal to 0. So the integrand then just becomes the integral, the surface integral over S1, y is equal to 0. So this is e to the 0, which is 1, minus z sine of 0. This is equal to 0. So this is 1 ds. Okay, so remember, go back and look in the section on surface integrals, or I mean, not on surface integrals, but when we first talked about parameterizations of surfaces, this right here, this is just the area of the surface S1. What is the surface S1? It's a disk of radius 4 centered at the origin, or sorry, centered at the origin of the XZ plane. But the important part is it's a disk of radius 4, so that's going to be 16 pi. Okay, so the point of this problem was that we used Stokes' theorem. We wanted to compute the surface integral of a curl field. We used Stokes' theorem not ultimately to write it as the line integral of a vector field, but to write it as the surface integral of a curl field, but over an easier surface. So that is the other way that we use Stokes' theorem. One way is to take a line integral over a curve and write it as a surface integral of a vector field over a surface. Another one is to take a curl field and instead of integrating over a harder surface, we integrate it over an easier surface.